Hello everyone, welcome back. Today we are going to talk about quantum NOT gates, CNOT gates, and the Z gates. In the end, we will have a practical example, a Python example that will show all these gates in action, how to apply it, measure the results. So that's at the end of the lecture. Stay tuned. So what is a NOT gate? A NOT gate is a with the classical analogy, like in the non-quantum computers, the regular computers, NOT gate and the quantum NOT gate is often similar. Okay, it flips from 0 to 1 and 1 to 0, which means if the bit value in the classical computers, if the bit value, if it was 0, it will change it to 1, and if it was 1, it will change it to 0, which means if the switch was on, it turns it off. If the initial state is off, it turns it on. Same thing the NOT gate does, or it is represented as X, the symbol. Same thing it does in the quantum computers or in the quantum circuit. So if the qubit state is 0, it will change to 1. If the qubit state is 1, it will change to 0. So if you apply the NOT gate to 1, the output will be 0. If you apply the NOT gate to 0, the output would be 1. The state of the qubit would be 1. This is the matrix representation of the NOT gate. If you're imagining the NOT gate in the block sphere, it changes along the x-axis 180-degree rotation. So block sphere is three-dimensional view, x, y, and z. So on a block sphere, if you're imagining it, it rotates 180 degrees along the x-axis. Now, what is its purpose? It's for flipping the qubit states, and it serves as a building block in many algorithms. Okay, so here is just a small thing, like if you pass 0 to an X gate, it turns to 1. Simple gate, but definitely useful. Now the Z gate. In classical computers, there is no equivalent of the Z gate. Okay, but in quantum, what it does is it acts it acts on the qubit only if it is 1. It changes the phase. It changes the phase of the qubit. Okay, so if it is 1, it becomes -1. If it is 0, it stays the same. So if you apply the Z gate, or if you pass a qubit through a Z gate whose qubit's value is 0, it'll come out the same. But if you pass a qubit with 1 through the Z gate, its value will be 1, but it adds a negative phase to it. So on a block sphere, it's a 180-degree rotation along the Z axis, so the vertical axis, the Z axis. So if you imagine a block sphere around, so along the Z axis, 180-degree rotation. This is the matrix representation of the Z gate. So if you're applying it and you're using it for matrix multiplication, you use this matrix. While it means subtle, the phase change introduced by Z gate is critical for creating the interference that affects the quantum algorithms. When we go further in detail and go through different quantum algorithms, we will see how the Z gate, NOT gate, and the C gate NOTs, the Hadamard gates, how all these gates are used in conjunction to create an algorithm. Now talk about the controlled NOT gate. Okay. Now it does have an equivalent in the classical analogy, which is the XOR gate, exclusive or the XOR gate. This is how its representation in the circuit, the CNOT gate. Now what it does, it works on 2 qubits. This is the important difference. See, it works on 2 qubits. One is the control qubit, The first one is the control qubit and the second one is the target, which means if you're applying the CNOT to this two qubits, see the first one is 0, the second one is 0. So it does not change the output. Now, if this is the qubit, first qubit is 0, with the control qubit is 0, the target is 1, no change to the target. But now see here, if the control qubit is 1 and the target is 0, it will flip the target. The control qubit leaves unchanged. See, in all the 4 scenarios, the control qubit is the same. Now, in this one, the target is also 1, the control is also 1. But what it does it flips the target to 0. So if the control is 1, only then it will flip the value of the second qubit. This is how it is used to create entanglement, which means that the outcome of the target qubit depends on the value of the control qubit. This is how they get entangled, create a dependency of one qubit on another. Okay. So by performing a CNOT, we can cause a system of multiple qubits to become a correlated systems. So the qubits are not just independent, now they are dependent or entangled with one another. This is the matrix representation of the CNOT gate. This is the circuit representation. This is the truth table, which we just saw here. See, there is a comparison between the XOR and the CNOT. It's the same. See, in the XOR also, the output, if it is 0, it becomes 1. If it is 1, it becomes 0. Same thing happens in the CNOT. It flips the target to 1. If it is 1, it flips the target to 0 if the control qubit was 1. But if it was 0, it leaves the target unchanged. Same thing here, leaves the target unchanged. So summary, the NOT gate flips the state of the qubit, like 0 is turned into 1, 1 is turned into 0. Z gate introduces phase change only if the state was 1. It turns it into a negative phase. The CNOT gate creates entanglement and performs conditional flip on the target. Okay. Now let's see a Python code with this example. Now here is the Python code. What you would need in order to run it. You would need to install Qiskit, Qiskit Air, and Platonix libraries, Python libraries. So you import the quantum circuit and transpile. You import the air, which we will use a simulator. So create a quantum circuit with 2 qubits. We're going to apply the Hadamard gate, and we are just going to print the circuit, how the circuit looks like. Then we apply the CNOT gate. See, this is how it is called, CX. This is the function, okay, with 0 as the control qubit and 1 as the target. And we print the circuit. We apply the Z gate to the first qubit. We measure the qubits, and we print the final circuit. We go to the backend simulator, we transpile, and the result, and we print the measurement results, like how many times it was 0, 0, how many times it was 1. Okay, let's see this in action. Here it is. I've run it a couple times, but let's see here. So I'm running this quantumgates.py using simple Python. Now here in my previous run, as you would see, 1 1 was 487 times, 0 0 was 537 times. The total of these two, it runs by default 1024 times. So let's see what happens this time. See, it has changed. 1 1 was 502 times, This is this, but now important is this is the circuit after you apply the Hadamard gate to qubit 0, qubit 1. Now what you're applying a CNOT gate to quantum 0 with the 0 qubit being the controlled one. Then you apply the Z gate to the 0 and the final circuit. Okay, you measure both of them, and this is how it is. Okay, the count, how many times it was measured as 0, how many times, how many times it was measured as 1, 1, how many times it was measured as 0. Let's run it one more time. See, the results randomly changed because we are using Hadamard gate, which creates it in superposition, and then what it means is the circuit 0 is superposition. It has the equal probability of being 0 or 1. So that's the randomness of the code. Okay. Now this would be there in my GitHub repository. You can freely download the code, try it, change it, okay, and practice it for yourself. All right, we'll be back with some more gates and more quantum algorithms. Stay tuned, and thank you for your time. Feel free to like, subscribe, comment. Bye.